Hello. In this presentation, I will share our work titled Enhancing SDN Security with a Feature-Based Approach Using Multiple K-Means, Word2Vec, and Neural Network. We will start with the introduction, where I will highlight the motivation behind software-defined networking and its security challenges. I will also discuss previous methods addressing these challenges and their limitations. Next, I will introduce the datasets used in our experiments and explain our proposed approach. Following this, we will explore the results. Finally, we will conclude with a summary of findings and future directions. SDN decouples the control and data planes, offering enhanced flexibility and enabling centralized control and programmability. This approach improves operational efficiency, supports scalability, and facilitates the integration of emerging technologies like Internet of Things, cloud computing, and 5G. However, SDN's centralized architecture introduces security risks, including data interception and unauthorized access. To ensure SDN's full potential and widespread adoption, robust security measures are essential to protect against threats and maintain network resilience. Numerous approaches have been developed to address SDN security challenges, particularly in anomaly detection and traffic analysis. For example, combining k-means clustering with k-nearest neighbors enhances DDoS detection accuracy, while k-means plus with fast k-nearest neighbors improves detection efficiency. In deep learning, deep neural networks and gated recurrent units are used for abnormal activity detection. Additionally, multi-layer perceptrons and feed-forward artificial neural networks have proven effective in attack detection, achieving high accuracy rates. Despite these advantages, several key gaps remain in the field of SDN security. First, many existing methods focus on clustering as a whole rather than analyzing individual features. Specifically, when using techniques like k-means, we don't consider each feature independently. This lack of focus on individual features can overlook valuable insights that could be gained by examining them separately. Second, there is a notable absence of hybrid methods that combine clustering and feature extraction to enhance detection accuracy. By combining these techniques, more robust models can be created, capable of capturing complex patterns and making more accurate predictions. Building on this observation, our work introduces a novel methodology. We integrate multiple k-means clustering models with Word2Vec for feature extraction, followed by classification using a neural network. This approach stands apart by analyzing individual features independently with k-means, offering a granular representation of data. In our experiments, we used two datasets, InSDN and CICD-DOS 2019. The distribution of instances for each class in our experimental datasets is illustrated in the displayed figure. Next, let's discuss our approach for constructing and selecting the optimal model. Each model incorporates multiple trained k-means models along with trained Word2Vec and neural network models. The figure displayed illustrates our methodology. For each k-value representing the desired number of clusters within a specified range, we build a model and evaluate its accuracy using the testing set. The model with the highest accuracy is selected as the optimal one. The steps for constructing a model using our approach are as follows. In step 1, k-means clustering is applied to each feature, excluding the target variable, with a separate k-means model created for each feature. The algorithm partitions the data within each feature into up to k cohesive clusters, treating each feature independently. Parallel processing is used to accelerate the training process. Afterward, each data point is assigned to a cluster, and the numerical data is transformed into categorical labels in the format attributes underscore cluster X, where X represents the cluster ID. This transformation converts numerical values into categorical data for further analysis. Next, we create a new feature called text. In this feature, each entry is a list of strings. To form these lists, we take the categorical values from the previous step, convert them into strings, and combine them. Finally, each list in the text feature is used as input for the Word2Vec model. In step 3, we utilize the Word2Vec technique, which creates continuous vector representations of words that capture their semantic relationships. We train the model on the text feature created in step 2. The dimensionality of the word vectors is set to 300, a standard choice based on existing research. Parallel processing is also employed to speed up the training. After training the Word2Vec model, we generate word embeddings from the text feature using the trained Word2Vec model. We iterate through each entry in the text feature, extracting word vectors for valid words found in the Word2Vec model's vocabulary. For each entry, we calculate the mean of these words vectors to create a single vector representation. If no word vectors are found in an entry, we append a zero vector. Finally, the word embeddings generated in step 4 are fed as input features for training the neural network, which performs the classification task. Next, we will present the experimental result, showcasing the performance of our proposed model in network traffic classification against a traditional neural network model. In the first experiment conducted without feature selection, we tested the impact of varying the desired number of clusters K. As shown, our model achieved a maximum accuracy of 99.97% at k equals 115, outperforming the neural network's accuracy of 99.77%. This improved performance is further reflected in the classification reports. Well, our optimal model achieved an F1 score of 1 for all classes except BFA, which achieves 0.99. In contrast, the neural network model exhibits a lower F1 score of 0.89 for the BFA class, likely due to its limited number of instances. In our second experiment, we extracted 41 relevant features from the InSDN dataset using select k-best. The selected features are shown in the displayed table. The proposed model achieved a maximum accuracy of 98.92%. In comparison, the neural network model reached a maximum accuracy of 98.05%. Furthermore, our optimal model demonstrated exceptional classification performance across all classes, with the precision ranging from 0.95 to 1, recall between 0.96 and 1, and F1 scores from 0.97 to 1. A key highlight is its performance in the BFA class, where it achieves an F1 score of 0.94, significantly surpassing the neural network's score of 0.65. In our third experiment, conducted on the CIC DDoS 2019 dataset, the proposed model demonstrates impressive performance, achieving a maximum accuracy of 98.65% at k equal 280 and 80, surpassing the neural network model's maximum accuracy of 98.01%. Lastly, as shown in this slide, our optimal model demonstrates exceptional performance in terms of precision, recall, and difference scores across several classes. Additionally, our model maintains superior metrics for classes with fewer instances, such as UDP lag. Our approach shows excellent performance across multiple network traffic classes, but it involves a computational cost. For the InSDN dataset, the overhead arises from the multi-step process used to construct models for each k value and select the model with the highest accuracy. As shown in this figure, training time generally increases with the desired number of clusters. Without feature selection, training times range from 328.79 to 841.08 seconds. With feature selection, training times are reduced to a range of 158.44 to 449.53 seconds. In conclusion, this study demonstrates the effectiveness of feature-based approaches in enhancing SDN security using advanced clustering and feature extraction techniques. Our model, combining k-means clustering, Word2Vec feature extraction, and neural network classification, achieved high performance on both the InSDN and CIC DDoS 2019 datasets. The results show the model's ability to capture complex patterns and outperform traditional neural networks, even with limited samples. While the process involves computational overhead, feature selection helps reduce this. Feature research will focus on testing the model in real-world networks, exploring alternative approaches for feature extraction, clustering algorithms, and classification methods, along with optimized parallel processing and the creation of a robust infrastructure to ensure scalability. Thank you for your attention.